is what we have. We assume it will be wet because over time when there's a long pipe or a tube that we stick into the exhaust pipe, water forms as we take reading. So we assume it's a wet exhaust gas composition. This is a reading we got in percent. My car, a Mazda 3 versus Dr. Henry's Civic Hybrid. There are some difference between the two numbers. CO, if you run it up to 1 sig fig, basically it's 0, but Dr. Henry's car has more CO2 versus my car. They are same in terms of methane. Methane is measured hydrocarbons. Instead of measuring hydrocarbons, they put in methane so they can tell the quantity of it. And O2, Dr. Henry's car is lower O2 versus my car. This is the material balance and the air fuel ratio calculation for my car. This is basically the equation for the reaction, which is octane plus a mixture of O2, N2, and then produces CO2, CO, O2, water, methane, and nitrogen. And you just make them equal, assume going in equals to going out. And then we assume it's ideal gas and complete combustion. For assuming it be an ideal gas, the volume percent that we measure equals to mole percent, so we can use it as composition. And this is the formula for air fuel ratio, mass of air divided by mass of fuel used. This is the number for it. Using the composition we got from the chart, we just use 13.2, I think it's the CO2. Yes, CO2. And then plus this is just the balance we did. I used the number, and this is the molecular weight of air, and this is just the balance of the fuel, of the C8H18. And divided it, I have a 16.0 kilogram air versus divided by kilogram fuel is the air fuel ratio of my car. This is Dr. Henry's car air fuel ratio. He has a lower air fuel ratio than my car, which means every 1 kilogram of fuel, I'll need 16 kilogram air to combust, and Dr. Henry's car needs 15.7 kilogram air per 1 kilogram of fuel. And this is the other experiment we did. Temperature of exhaust gas versus different cars. We did Civic Hybrid, a Ford van, UTC Sport van, and a Mitsubishi Outlander. We have 2 exhaust pipes in that car, and a BMW and a Chevy truck that is modified. Temperature in each car temperature of the exhaust gas coming out of each car is different from the graph reading that we found. We also measure the velocity of the gas coming out of the car. The Chevy truck, I'm going to start from the highest one going down to the lowest. From the owner of the car, the Chevy truck is modified. The person actually took off the catalytic converter to it, so produced a lot of hydrocarbon, but we have no idea why he did that. Apparently he lives in the area we don't need emission checks, so he took off the catalytic converter for it. And the BMW is the second one to the highest, and then it goes down to the Civic Hybrid produces the least velocity of the exhaust gas. I assume it's because it has a lower running power versus the other cars. They run on half electric versus all full fuel. We also measured the diameter of it, and of course he also modified his tailpipe to like a 5-inch diameter pipe, so I assume it can produce a lot of hydrocarbons. And this is all the other measurements for the other car. And then we calculate the graph of the emission quantity per time for each car. And still, he produces the most pound per hour of the emissions on nitrogen and the others. And these are too small to be determined, so they're basically just running off to be 0. And the Civic Hybrid again has the smallest mass flow rate of emissions. I assume still because it's half power of electric versus a full field engine. And this is a discussion of the results that I found from the graphs. Every car has a different exhaust gas velocity, and the emission quantity per time for each car depends on their exhaust gas velocity. If you look at the graph from before, the velocity goes from the highest to the lowest right here, from the Chevy truck to the Civic Hybrid. And then if you look at the emission quantity per time of each car, you can see right here is also the highest for each component going down to the Civic Hybrid. In conclusion, Mazda has an air-fuel ratio of 16, which means 16 kilograms of air is needed to burn 1 kilogram of fuel. Civic Hybrid has a air-fuel ratio of 15.7, meaning 15.7 kilograms of air is needed to burn 1 kilogram of fuel. Means there is not much difference in terms of engine performance between two cars, so not necessarily need to buy a hybrid versus a regular car. The higher the exhaust gas velocity, the bigger the emission quantity per time. And this is my reference, Dr. Knight, that show us how to use the gas process analyzer to measure the composition coming out the car exhaust. Is there anything, questions?